Well, that's fun.
Morning, Doug.
Morning, y'all.
What did Connor get on his test?
We're all waiting to hear. You did awesome. Only missed a couple of points.
No.
Oh, a couple, Connor, a couple. Ooh.
How many, Doug? How many points?
I posted it last night, way late, or in the afternoon. It's in my open math. I put your scores in there, and I wrote all of your tests and put it back into my open math. So it's in there right where you.
Yeah, I'm hitting refresh. It's not updating, or it's not showing. The fact that you had to write all over it is concerning for me, though.
No, it was good. 97%.
No, 97. Oh, David won by 1 point.
Connor, it's okay. Don't worry.
No, I'm coming for you in the final, dude. I swear to God, I'm getting it.
You're gonna have to study.
That's awesome. I'm gonna take a quick look. Really, I don't understand. That should be in there. Grades. Grade. Well, you're not wrong. You are not wrong. It is not in there. Don't know why, but it is not. Put your score in there, but I will link your test up in there later.
If I wasn't wrong about this, I might not have been wrong about those 3 points on the test for sure, right?
Oh, that's right. Absolutely right. Well, good morning, y'all. So here's a flash look at your test, Connor, because that's what I just opened up in my iPad.
Yes.
And there it is. Look at that.
So where was the mistake? That's my question.
Oh, with the one we were talking about.
Oh, was that it? So why, even though it matched on Desmos, why did it come out wrong?
Don't completely know. I mean, so you just lost this negative sign. You had a negative sign there. And you lost it. The end result. No, I can figure it out. I mean, so you have 29 and 24. If T is 0, that'd be 29 and negative 24, which is positive 5. I have negative 14 and positive 9, which, when 0 would be negative 5. That bugs me. I mean, it's still we're talking about the coefficients. My first thought was all the coefficients. That's the C1 and C2, and so they're all family answers. They're all answers. Any constant you put there would be an answer, but it shouldn't cross at the right point. Like whatever the original.
Yeah, cross at 4.
0 equals 0 and y prime 0 equals 6. Like that shouldn't work. But the fact that it laid right over the top of the right answer, though, what? I don't get it. I actually couldn't figure that out.
Dang. Oh well.
I have a feeling there's actually a fairly simple answer to it, but and I can't remember what I took off on that question, which it wasn't very much, if any at all, just because you did check it and so forth. So you'd have no reason to think there was anything amiss.
Yeah, it sucks to get it like so close to right that I move on. I'd rather just bomb it. That way I can go back and be like, something went wrong here.
Right. Yeah. No, I mean, you're going to lose signs on this. Most of the mistakes. I mean, I'm pretty happy with everybody because people's mistakes were small and algebraic, and that's not that weird. Okay, so I wish I had followed my own note and done this with you yesterday so that you had more time. The project is really cool, but it's really tough. So we were talking about this after class, but not everybody was there for that. And so you're sitting here with this, So I'm going to give you a kind of a world-class hint now. So you're sitting here with this, and I gave you a shot at kind of understanding where that came from and, you know, why that was a model. And again, we're disappointed to discover it's got a first and a second derivative in it, and that's all we got. And so you know, your first glance at that might be, well, I don't like fractions. I could multiply both sides by a, and I could square both sides to get rid of the square root. And those are actually pretty good ideas. So if I squared both sides, then wouldn't I have that? But that doesn't really take you very far. In other words, I still don't know what to do. And so here's a huge hint. Or a kick in the right direction. And honestly, I would expect everybody to have got stuck on this. I mean, unless you're just a brilliant person. If you made progress with this on your own, and frankly, that's what I wanted to give you time to do. This was rather than kind of let you off the hook too early, give you some time to think about that. Because I have had students make progress with this on their own, which again, to be, you know, blunt with you guys, like I'm not the kind of student that would have done that. I'm not the kind of student that thinks up things. I'm not, and actually, I don't remember even how I got this answer. I don't know if I figured this out myself or not. I can't remember. But these squareds right here are really a problem. Do you understand that? Like, if those weren't there, then we'd be like, oh, cool, a second order differential equation. I'll subtract y prime to the other side, and, you know, then I can solve this second order. But that's squared. And so, you know, I've never had that happen before. And again, in the language of this class, we've mostly been solving first and second order linear differential equations, and those squareds right there make it not linear. Like, isn't a line y equals 3x plus 2, but then if it's y equals 3x squared plus 2, then it's not linear anymore. It's not a line anymore. And so this is not a linear differential equation. This is really problematic. We don't have any techniques to solve this right now. And so, you know, you might think, well, how do I get rid of squares? And, you know, you can square root both sides, but then you get back where you were a second ago. And there isn't any good algebraic way to get out of that mess. But remember, this is an equation, and you can do the same thing to both sides anytime you want. And so my hint is this. Take, and I shared this with a few people that were left yesterday that asked me after class, but take the derivative of both sides. And I want you to think about that. Like, why is that? First of all, it's like, yeah, I can do that. I mean, I was thinking algebra, but can't I do calculus to both sides? But why is that really cool? What would taking a derivative of both sides accomplish? Why would that? And again, that comes from left field. Like, why would you think to do that? But what does a derivative do?
Pulls that 2 down front.
Yeah.
And then you multiply by the junk inside, right? The derivative of the junk inside.
That's exactly right. So it's the chain rule. So you say, hey, junk squared. What's the derivative of junk squared? 2 times the junk unchanged, right? You don't change anything inside. So that junk inside is still the same. But the cool thing is this goes down to not a derivative, but to the first power. In other words, that's not there anymore. Does that make sense? And so, cool. But chain rule says you're not done. You have to multiply by the derivative of what's inside, right? What's the derivative of what's inside? Remember, a is a constant. Somebody say it out loud.
A times the third derivative of y.
Exactly. So the a comes along for the ride, and the derivative of anything is just add a derivative. Well, there's already 2. Well, now there's 3. Now, again, that seems like this isn't going anywhere. And then the same thing happens on the other side. The derivative of 1, though, is gone. But now you can do algebra, like, you know, y double prime is an animal, y triple prime is an animal. Like, you can do the same thing to both sides. You can add them to both sides. You can multiply them to both sides. You can divide them. This will get you out of the weeds. So there's my hint. This is due tonight. And so you already know the right answer to this in the sense of where it's going. You know what it's supposed to produce if you succeed in getting rid of all these. And of course, it's intimidating that I just got a y triple prime. However, didn't you just do one of those on the test? And you have two methods now. You have a guessing technique to solve differential equations, and you also have a Laplace transform technique. And in the end, Laplace transform will give you one, and the guessing technique will give you another. That's where kind of both answers come from. Second thing I want to say, just by way of a hint, is remember what this graph looks like. Because there were no initial conditions given. But remember, the graph looked like this. It went through the point 0a, and it looked like this, which means you should be able to tell what those initial conditions are. And again, that was taking the answers, what this graph looks like. Again, it looks like a parabola, it just isn't one. But its bottom is right on the y-axis. It levels out, flattens out right on the y-axis, and that a value, it hits right there at 0a. And so you actually have the initial conditions from the graph that So think about those two things. And again, I really would love everybody to get it as much into their own power as possible. And I'll, meet with you after class and put some more thought into this. But I'll give you that hint and then give you some more time to think about it. Sweet. Okay. So yesterday was the introduction to solving systems, and today we're actually going to learn a technique, kind of a cool technique for solving systems. Differential equations. And again, systems, you're far enough in math, you want to have a kind of a good conceptual understanding of something. A system is, I mean, even if you just think about, like, you tried to write a definition for the word in some English class, wouldn't you think that's like a bunch of stuff? A system is like, things, I'm making this up as I go, like things that are connected. Like I've got, I'm working on this thing and that person's working on that thing, or I've got, like a machine and it has this system over here that dries the clothes and this system over here that washes the clothes. And like what makes it a system is it's got kind of a lot of parts to it. Well, a system of equations is just, you got more than one equation, and by kind of definition, they've got more than one unknown. So this time I'm going to make one up, or maybe I probably stole this from the book. I have it written in my notes here. It's probably one of the questions in your assignment that I didn't assign. So that's not good because it's got not one unknown, not two unknowns, but actually three. And remember, the overall goal here is to find these equations. Remember, x is actually some function of t. And we'll get rid of this, but it might be like the sine of t or the sine of et squared or something. X is some function of t and we don't know what it is. That's what x represents. And so for y as well. So those are functions of t that we don't know. And then e to the t, fine, that's a function of t, and so we're okay. And so that's got three unknowns to it. Ultimately, since the independent variable is t, I'm okay with t being there. I mean, like, we've been solving differential equations that had y's and t's. In other words, it's kind of okay to have two unknowns, the y and the t, but I can't have yx and t. And so the system comes in where you say, well, that's not the only system here. There's another one. And so here's the second one. X prime plus y prime plus 2x plus y equals e to the t. And if I didn't get rid of it, which it looks like I did not. Yesterday, we had these two red equations. And we didn't need to learn anything new to solve them. Like we figured out a way. Ben gave us a good idea that ended up working. It's the first one to think of something that we could do. And so if I remember right, we solved the bottom one for y. So we solved the bottom equation for y since it was just a y. There's not a y prime there. So we solved it for y. And then we plugged that value in that we got. We plugged it in here. And then we said, well, what are we going to do over here? Well, hey, that's a derivative. So couldn't we just take the derivative of our y equation? And then we, because of that, had an equation with just a bunch of x's. And so that was really wonderful. But why is that not going to work so good today? There's a little more going on. But for instance, in the second equation, the fact that there is a y term, but also a y prime term, does it make sense we're not going to be able to solve the bottom equation for y like we did before? Because we have a y and a y prime. So there's no way I'm going to be able to do that. And so yesterday's method isn't even going to work for this. It's not just that, you know, today I'm going to show you a shortcut. No, today, if we used yesterday's techniques, we can, you know, do things to cancel things. You know, as a, for instance, if I said, hey, I'd like to get rid of this x prime term, well, then I could multiply this whole thing by -2. And then when I added in, the x prime terms would be gone. But would that be sufficient? And the answer is, well, no. Maybe I'll write this down and leave it here. But if I added those together, let's see, I'd have y prime -2y. I got to be a little careful here because, you know, these would have to be on the other side of the equal sign like these are. So I'll just kind of do that in my head. So that'd be a -2x on the other side. That'd be -4x added to x. That'd be -3x over there. And that'd be -2y added to y. That'd be -y. And then notice that's e to the t and e to the -t. Therefore, I can't even add them. So that's okay to do. That helped. I got rid of x prime. It's not as ugly as it was, but I didn't get rid of this. I mean, this is the one that's kind of the holdover that I'm kind of disappointed about. I could have solved this problem if that hadn't have been there, because I just have y primes, y's, and t's, and that would have been okay. But that x is kind of a killer. And so in this problem, if you just use the technique of elimination or some kind of substitution, you're never going to be successful getting rid of everything. You can make progress, but you can't get it to where there's only two unknowns in that equation, kind of your y function and your independent variable t. So what do we do? Well, turns out there's kind of a really brilliant technique to this. So won't work. So if we just think about a derivative, like when I say derivative, don't we even write derivative of x as like dx? In other words, x prime would be dx dt, since our independent variable in this problem is t. So, you know, d is an operator. In other words, you're saying take the derivative. And of course, somebody that hasn't spent a lot of time in calculus would think of that as d times x, right? Because that's just some other letter. But we're thinking of that as an operator, right? It's an operation, that letter D for derivative. It isn't like a variable. It's not a constant. It's actually an operation. And so we're going to take the derivative of x with respect to t, some x equation that's made of t's. We're going to take its derivative. Well, that's all we're really going to do here. And I want to watch what follows from that. So all I'm going to do is rewrite this. I'm going to say 2 times dx. Oh, there's that cool Laplace transform trick too. Maybe I'll go into that. Forgot about that cool trick. So instead of saying 2x prime, I'm just going to say 2 times the derivative of x. I could use lowercase d or uppercase d, it doesn't really matter. 2 times the derivative of x plus y prime, or the derivative of y. And there's no derivatives on the other side, so I don't do anything over there. Again, it's not that I'm taking the derivative of both sides, I'm just rewriting it. Now, of course, you should think, you know, what good is that going to do? Because you didn't do anything. You just rewrote it in some different way of saying derivative, and you're not wrong. I didn't do anything. Second equation, then, the x prime would be the derivative of x, and again, the derivative of y. And I guess maybe I'll move all the stuff on the other side, just since that's the way I'm used to seeing it, but I actually don't know if I need to do that or not. So would you agree nothing has been accomplished, and this is, if you will, kind of a bad idea, or it looks like a bad idea? But here's something kind of cool now. What's kind of cool is before I had to look at this animal and this animal is sort of like different, right? Like they're both x's, but one is x prime and the other is x. And so I can't do anything with them. I can't add them together. I can't collect them. You see what I'm saying? I can't, but here's what's kind of magical about this. Now, all of a sudden I can. In other words, if I rewrote this now as 2dx, but then I bring that x over there with it, subtract it to the other side, and then I have this plus dy, but then I've got a y term and I subtract it to the other side, and so all I have left is e to the negative t. Then do you notice the x is now kind of just an x? And so if I think of it as, all right, well, then I'm going to factor that x out, leaving 2d minus 1. And I'm going to factor that y out, leaving d minus 1. And notice there's got to be a 1 there to kind of hold its place. But again, d is not a variable, it's an operation. This is operator form because d is an operation. And yet we're sort of treating it like it's a letter. Does that make sense? It's almost like we're saying it's an operation, but we're going to, you know, put it off till later. We're just going to do that operation sometime down the road.
So is capital D d over dt because the x came out?
Yeah, it's just another way of writing dx dt. Like I haven't really done anything different. In other words, maybe I'll just write that here, like d equals dx dt. I mean, it's just a derivative. It's an operation. It always was, nothing new. And actually, I should say dx is dx dt because dy would be dy dt. So my point is nothing fancy has happened here. I haven't done anything earth shaking, just writing it in kind of a second. Cool, so that's kind of like my first equation here. So there it is now, kind of completed. But you see that what's kind of cool about saying, I'll just worry about that derivative taking later. I used to have 2 x's in my equation, and now I just have 1. You see, that's kind of cool. And that's what's going to allow us to now actually do the substitutions and eliminations that we've done before and actually make some progress with this. And so it's kind of a cool sleight of hand, I guess you might say. And so then what about the second equation? Well, then that, of course, would be if I have dx on the left side, and I add the 2x, and so I didn't really want to put that on the other side, just leave it with itself. Add the 2x back over there, and then I've got dy on the left side, and then I'll add my y back over there and just leave that e to the t alone. And then again, factor out x, leaving derivative plus 2, and factor out y, leaving derivative plus 1, and nothing changes on the other side. And so now I have kind of my second equation. This is what your book anyway would call operator form. I've got this thing in operator form now. That's kind of cool. And again, I haven't really done anything. I haven't changed anything. There's nothing weird going on, except, as I mentioned, hey, those forms now, there's only 1 x in them. There's only 1 y. And so could I then get rid of one of the letters now? Well, the answer is I can do that now in a way that I couldn't do before. And so, how am I going to do this? Well, maybe I'll do this. If I took equation 1, I'm going to try to get rid of x. I have no good reason for that. Should I get rid of x, get rid of y? I don't even really see a difference. If I took that first equation, 2d minus 1, and then I recognize this one down here has a d minus 2, then if I multiplied this top equation by d minus 2, and then I did the same thing with the bottom equation. If I said, hey, there's an x and then a d plus 2, but then I multiplied it by the one that's missing in the top equation up there, 2d minus 1. Does it make sense? Those are the same thing now. So again, this is no different than you sitting here back in the day saying I got 5x plus 3y equals 7, and I've got 2x plus 9y equals 8, and you're like, oh, let's add those together to make something go away. Well, nothing's going to go away right now. Well, how about if you take the 2 that's down below and multiply it by the one on the top, and the 5 that's on the one above, multiply it by the one below? Notice they're both going to be 10x now. Now, in this case, you'd have to subtract, but if you picked one of them to be negative, then you could now add those and you'd have negative 10x, positive 10x, and then your x would drop out. That's all I'm doing. Does that make sense? I'm just doing it with operations. Now, notice that's adding a bunch of operations. Like, remember, d is not a number, so I'm just adding a whole bunch of operations. I got to do a bunch more operations. So, you know, algebraically, of course, I got to do that to every single term, right? So if I multiply this top one times d plus 2, then I've also got to do it to the y. And I've also got to do it to the e to the negative t. And so I multiplied top one times d plus 2. I'm going to continue to multiply the bottom one times 2d minus 1. That was already a d plus 1. Now it gets multiplied by 2d minus 1. And the e to the t also gets multiplied by 2d minus 1. And so you could subtract now if you want to, but people tend to make more mistakes with subtraction than they do addition. So I'm just going to pick one of them to be negative. So if I go through and multiply everything by -1, I guess I'll just pick this one. So that's negative, and instead of erasing it, I'm going to throw negatives in front of that stuff just so that you can see them there. And I think I'm even going to go back and do that in a different color just so it kind of stands out to you. It's like, oh yeah, I guess I got to do that too. And so now I'd be able to add these together. And so do you agree that there's going to be no x's now? Like, it seems like I'm going to have a giant disaster left over that is a bad idea, and like this isn't going to work, but at least there isn't going to be any x's anymore, right? So I guess I would have, well, let's leave it alone. I'm going to write it like this: d minus 1 times d plus 2 times y. That's that top term. And then it'd be minus d plus 1 times 2d minus 1, also times y. And on the other side of the equal sign, I'd have d plus 2 times e to the negative t minus 2d minus 1 times e to the positive t. Need a little more, a little bit more real estate. E to the positive t. Do you agree with that? We all right algebraically? Haven't done anything wrong? So if you're a person that likes steps to things, I'm not. I like to just think, but kind of step 1, operator form. Get it in operator form, because that effectively took what used to have 2 x's, only has 1. Second, eliminate x or y. That's kind of my second step. So the question is, what do I have left? I mean, there's a part of me that wants to celebrate, like, yeah, I got rid of X. Now I can solve this problem. The other part of me says, I don't even know what I have anymore. What is that? Like, I don't even know what I'm looking at. Well, let's think about that for a second. Maybe you see this already, maybe you don't. Let's see, if I distributed, this and multiplied it out, I'd have D times D. And then I'd have minus D plus 2D, so that'd be plus D. And then I'd have minus 1 times plus 2, that'd be minus 2. And all of that is still multiplied by Y. And here I'd have minus D squared, 2D squared, plus 2D minus D, that'd be plus D, and then minus 1. And that's multiplied by Y. And then no change on this side. So the question is, what does that mean right there? What is this animal? What is this thing? Is that something I can do, or am I confused by what I'm looking at there? Well, I'm not. Are you? Well, if you just distribute this in here, D squared Y plus dy minus 2y minus 2d squared y minus dy plus y equals d e to the negative t plus 2e to the negative t minus 2de to the t plus e to the t. Did I make any dumb algebra mistakes there? Distributed my negative signs. Now do you see it? What did we decide back here that, this meant? And all we did was take that and rewrite it like that. All dx means is the derivative, right? So then let's just stare at what we got. And even before we do that, let's clean up the algebra a little bit. Like, notice I have a plus dy minus dy, like that goes away. That's kind of cool. And then I have a plus d squared y, whatever that thing is, minus 2 of them. So isn't it minus 1 of them? And then minus 2y plus y is just minus y. And I guess I can't do anything on the other side. So that all stays the same, but I didn't fit it on one line. So I'll quickly rewrite it. But again, isn't d just a derivative? Doesn't that mean just take the derivative of the junk that you see looking at? Or the d, this is like de to the negative. Doesn't that just mean take the derivative of e to the negative t with respect to t? That's exactly what it means. Like, so let's go do it. In other words, doesn't this right here just mean negative? Seems like it's time to switch color. Doesn't this right here just mean negative? Well, take the derivative of y twice. Isn't that what d times d means? dd, like d squared means dd, right? D times d. So that means take the derivative of y twice. Well, isn't that y prime? Derivative of e to the negative t is negative e to the negative t. Notice there's no derivative here. It's just 2e to the negative t, and I can put those together. And then negative 2 times the derivative of e to the t, but the derivative of e to the t is just e to the t. And let's see, I don't like negative signs, so I'm going to do two things at once here. So I'm going to collect the junk together on the other side. That would be plus negative e to the negative t plus 2e to the negative t would be plus 1e to the negative t, but I just multiplied both sides by negative 1. And then this would be negative e to the t, but then I just multiplied both sides by negative 1. And so Like, look what happened. And so I put it in operator form to really make what used to be two x's, one x and then one x prime to just be x. And in that way, I was able to eliminate something. And now I have a differential equation that I can solve. And at this point in the class, in your knowledge, you're sort of free to solve that in any way that you want. Laplace transforms or guessing, whatever makes you happy.
It's probably just me, but I'm confused at the last bit of algebra you did, the very last.
Yeah, I did two things at once. I looked at these two. So would you agree? I'll write one preliminary step here. Just so
You multiplied by -1 and then what?
So I just looked at these and said, hey, look, like terms, -1 e to the negative t plus 2 e to the negative t, that'd be e to the negative t, right? And then this one here, I said, look, -2 of them plus 1 of them, that'd be -1 of them. And then I just said, well, look at all these negative signs. I hate negative signs. So let's multiply both sides by -1. And so
Gotcha.
I just did two things at once, which made it look confusing.
Okay. It makes sense, but the operator form feels illegal for some reason. I don't know
I
why.
love that. That's a wonderful statement you just made. In a sense, because we never did anything with them, it's just kind of a cool idea, isn't it? I mean, but we never did anything. We just kind of said, well, let's wait till later. We agreed that D, I mean, even if you think of, for instance, we ended up with d squared y. I mean, if you say, well, d squared means d times y, but again, it's not so much times, it's an operation. It's not d times y, it's the derivative of y. So then I look at this and I say, well, the derivative of y is y prime. Well, what's the derivative of y prime? Well, isn't it y double prime? And so it's weird, like just by writing it in that form, all of a sudden we can make progress but it's kind of cool that it actually created, if you will, a d squared as a result of getting rid of these operations. But you're exactly right. I love the way you're saying that. It feels illegal. It feels like somehow we shouldn't be able to do that.
All is well that ends well.
Yeah, and of course, in a sense, the proof's in the pudding, right? Because if we go on to solve this problem and then we, come back here, as soon as we find our value for y of t and x of t, as soon as we find these two values right here, and then we, actually plug them back into this, and it's like, oh my God, that actually worked. I can't believe it. That's exactly what you said. The proof's in the pudding. Like, I guess it does work. But it's pretty nifty. Again, I find myself just thinking, who thinks of these things? I mean, I don't know about you, but I would have just stared at that. I mean, if I would have stared at this original problem for forever and just went, I don't know what to do. But again, don't forget, the thing you overlook is that people that invented this stuff, 200 and 300 years ago, were people that had more time on their hands, and they were also really smart people. And they probably didn't figure it out in an hour. You're used to doing math where the teacher explains it, you go away, and then you're supposed to kind of immediately be able to do all the problems. And ideally that's kind of what happens, but real mathematics is where you just bang your head against the wall. It could have taken somebody 6 months to come up with a method for this. And remember, you're also trying to come up with a method, not aware if there even is one. It'd be different if somebody says there is one. Don't give up until you find it. That's kind of what I did on the project. Yeah, there's a way you can do this. There's a way that this can be done. That gives you some hope. But if you're the first person to invent something, you're just thinking, I wonder if there is a way. And again, notice we're making up an equation here that isn't modeling anything. This isn't useful. It's just somebody saying, I wonder if we can always do this. Is there some way you can always solve systems of differential equations? And based on this operator idea, at least from what we're seeing, it seems like the answer is, yeah, well, yeah. Let's see, I'm trying to decide what to do now. Do I take the time and just solve this, or since I already solved it, do I just tell you the answer? I think it makes more sense not to solve this. So let me go back to the start and just add in some initial conditions to this, because that is one part of this that isn't obvious. And so we do need to think about that a little bit, because you might have remembered yesterday that was a little bit weird. Notice these are first order differential equations. And so knowing where you started, x of 0, x at time 0 is 2, and y at time 0 is -1. That's got to be given. And of course, that's, again, sterile in this case, whereas in the project, not sterile at all. We're just throwing that in there. But as we saw yesterday, notice this created a second order differential equation. And so that's not so good. So let's see, my notes are clear here. So if you chose the guessing technique, do you agree you're going to get 3 answers to this? There's going to be, well, to start with, it's going to be like, this is the part I'm going to skip. So you'd have, y, I guess we'll call it y1, kind of the homogeneous answer. And because this is r squared and this is +1 = 0, isn't that your auxiliary equation? So you end up with r equals plus or minus I. So then based on that, let's see, based on guessing, wasn't this was kind of our E value. It was like e to the 0t. And then that 1 that's in front of I, because notice it's not 2i or 3i, that was kind of the sign. It was like sine of 1t. Isn't that the way our guess worked? So the result of that homogeneous answer would be C1 sine of t plus C2 cosine of t, because it's e to the 0 since this first part of the complex answer was a 0. So it's e to the 0t. Oh, okay, there isn't one of those. Fine. In case it screws me up, just since I'm skipping a bunch of stuff, I'm gonna put C1 with cosine and C2 with sine, just because that's why I looked over at my notes and saw what I did. And so that's our homogeneous answer, right? And so there's our unknowns, and that's where the x of 0 and y of 0 are going to get involved. But then you have your guesses, right? So, and notice there's two more answers, because there's 2 guesses to this. So I'm going to have my, a e to the -t guess, right? And then I'm going to take its second derivative, plug it in, solve for a, and so forth. And that's going to come out with a particular answer to this. And that turns out to be -1/2. So I'll say ... plug it back in, and you end up with y2 equals -1/2 e to the -t. So there's y1, there's y2, and then the same thing happens for y3, except for we have a different guess. It'd be b e to the +t, and I, again, take the second derivative of that, solve for b, and I get 1/2 for that. So ... b ends up 1/2. And so you would then say, okay, great. I just found my, I guess we said this is our general solution for y. And I just, write all those added together. So C1 cosine of t plus C2 sine of t minus 1/2 e to the -t plus 1/2 e to the t. And so cool. But then what about these conditions? How am I going to get those involved? And so we got to think about that. And then the second one is, how am I, remember, I've made a ton of progress now, and I now can kind of say, bam, I got my y of t equation, sort of mission accomplished. It's general, and I don't know what C1 and C2 are, but at least I got that far. Well, does it make sense I still have to go get x of g as well? And so what would you do? Because this is the part that's kind of new. what would you do to go get that now that you know this answer? Or should I be plugging in those, initial conditions right now? I forgot what they were x of 0. I'll rewrite them right here. X of 0 equals 2, y of 0 equals -1. I mean, should I be plugging those in right now to get C1 and C2, or can I even do that? I mean, what's going to happen there? Or should I be going to get the X equation? So what are your options to go get the X equation? Well, remember, I quite randomly decided back here that I was going to eliminate X, right? I didn't really have any good reason for that. It wasn't any faster, but I could just start all over and eliminate Y, right? Since the Y had a D minus 1 and a D plus 1, then I could multiply this one by D plus 1 and this one by D minus 1, do the same thing to both sides, start all over. I'm going to get a second order X equation, and that'd be great. Absolutely nothing wrong with that. But is there any way, and we did this a little bit yesterday, but is there any way that I could do this any better, any faster? What could I do considering those original equations? Because remember, I know what Y is now, and this is kind of what we did yesterday. I know what Y is, and so how could I get X? Well, if I knew what Y is, I could plug it in right here for Y. And I could plug it in here, but I'd have to take the derivative of it. And then I would have no more Y's because I'd have T's, right? Because isn't my Y a function of T? So I just have a bunch of T's. I have an X prime and an X and a bunch of T's. Then notice it's only a first order differential equation. So I could solve that now and it wouldn't be quite as hard. A first order is not quite as hard to solve. Does anybody see even a better place to plug it in though? Notice it's not here because this is the same. I could plug it in there, plug it in there. It's the same kind of thing happens. But where's an even better place to plug this in?
You plug it in down below, I guess, as long as you like the red equation, but you have to solve for, you like take Y out of it and solve for X's instead of Y's.
Yeah, that's exactly right. Like this is a great place to plug in our Y of G function because notice there's no X prime in it. And I didn't do that on purpose. I was just showing you that won't work. That's the only reason I did that. But it's just kind of cool to notice if I plugged it in here, then I wouldn't even have to solve for X. I wouldn't have to think about X prime and X. It's like there isn't an X prime. So great, now I'm done. So in hindsight, I think I'm going to plug it in there. That seems kind of cool. But let's go ahead and do that.
I think that for that equation, it might be 5x and instead of -3x.
Awesome. So you made an algebra mistake, and now that's going to matter.
Maybe adding on
And because Ben is telling me that, I'm ready to bet against myself. So let's see. No, because, well, I still might have screwed this up, but the equal sign, again, I kind of did what I did earlier. I did too many things at once, but the equal sign is here and here. So you got to be careful when you add those. I can't just add these because this X on top is on the right and the 2X is on the left. So in my mind, and I might have screwed this up still, and because I kind of did too many things in my head. And again, because Ben brought this up, and I know Ben pretty well, I'm guessing I actually did screw it up. So I multiplied things through by -2. Let's see if he's right. And this would become -4x, right? But then I'd have to move it to the other side. So it'd be a +4x, and then 4x and x would be 5x. And so he's exactly right. So let's go back and fix that. It's a good argument to not do too many things in your head. So let's see, this would be -2y, but then I add it to the other side and it'd be 2y over there, and 2y and 2y is 3y. And so, yeah, I did too many things in my head and screwed it up. Do you see anything else? Since you pointed that out, Ben, it looks like everything else is okay. Yeah. Thank you, Ben. And again, I kind of like to make those sorts of mistakes in front of you because as I often work, and then, you know, I'm gonna stare at this mountains of work and I have no idea where I screwed it up, and it's probably gonna cost me more than a half an hour. And temperamentally, that's a mistake. That's a type of mistake I personally, based on my temperament, make a lot. So I'm just being lazy. I just want to try to get this done. It's kind of the easiest way possible. So okay, well, in order to do this, because I also need y prime, I'm going to go find y prime of g. So let's go figure that out. Maybe that'll be hopefully not too terrible. I'm just going to leave the c's in it for now. I don't know if I should be trying to solve for those or not, but the derivative of cosine is negative sine, and the constant comes along for the ride. The derivative of sine is cosine, so that doesn't change anything. The derivative of e to the negative t is e to the negative t, but then times -1, so that would turn that into a plus a half. And nothing changes in the other one, because the derivative of e to the positive t is just e to the positive t times 1. So there's my first derivative. And so cool, if I take that, so I take then this mess up here and stick it wherever I see y, which is right there. And I take this mess right here and I stick it wherever I see a y prime, bam, right there. Let's see what happens. So I got to change, it says negative y prime. So I got to change the sign of all that stuff. So I got C1 sine of t plus C2 cosine of t, except for I didn't change the sign like I just got done saying. Change all the signs. Minus a half e to the negative t minus a half e to the t. So there's the left side, and then I got 5x. I don't do anything with that because I want x's. And then plus, this is never fitting on one page, plus 3 times all that junk. So 3 times c1 cosine of t plus 3 times c2 sine of t minus 3 halves e to the negative t. 3 times a half is 3 halves e to the positive t. So that's all plugged in here. And then I just have these last 2 terms to kind of tack on to the end. And they're not multiplied by anything.
Would
so
the 3 halves e to the negative t be positive?
3 halves, would this be positive? Did I blow it? Did I blow it? Did I blow it? No, because it was negative up here. Unless I, again, I could have lost a sign really easy, but it was negative up there, but I just multiplied it by 3.
Oh, okay.
Thank you for speaking up. And I found myself, staring at what I got, thinking, man, I can't really keep track of what I have here very well. So it's like rewrite that negative equal sign nice and big. And so despite the fact that that looks, a little intimidating, notice like the main thing I'm staring at here right now is that x right there, right? Don't I just need to solve for x, and it's not x prime, and that's the only x in the house. So all I got to do is solve for that. And notice you got all kinds of like terms here to collect together. So since that at 5x is already on, it's positive and it's sitting on this side by itself, I'm going to rewrite it on the left side since that's where I'm used to seeing it. But I'm going to basically disappear all these things over to the other side. But let's try to be a little careful. So let's see, if I take this, then I'd be adding 3 halves, and then this is my like term right here. So 3 halves and a negative half is positive 2 halves, and so that'd be 1. So that's e to the t, and so that takes care of this term and this term. But then I have another one of those, right? So I'd be subtracting that to the other side. Am I right? Is that gone? Yeah, it is. There's none of those left, which I'm sort of glad about, right? So what about my e to the positive t terms? Which colors? Again, this is dangerous. So if I subtract this to the other side, that'd be negative 4 halves e to the t or negative 2e to the t. And then when I add this to the other side, it goes away as well. Is that really true? Like all of those are just gone? Feels like a book problem to me, like, wow, that's unlikely. I'm also doubting my algebra. Let's see, that'd be negative, just to double check myself, this would be negative 4/2 plus 3/2. This would be negative 1/2 on this side. If I added it together, yeah, I guess that would cancel. So I don't think I made any mistakes there. So then I got some sine t's. I got a 3 sine t on this side, 3c, and then I've got a 1c over here. So I guess I would have, if I subtracted it over, I'd have c1 sine minus 3c2 sine. So there's my sine terms. And then if I subtracted this away from that side to go with my other cosine over there, I'd have negative c2 that's already over there, and then I'd be subtracting 3c1 over there. And then I just divide by 5. Check my notes. Is that really, it just does not seem right. It just feels like. So then I guess I could say then that my x of g term is all of that except for just divided by 5. So let's copy it. Go back here and kind of highlight this one again. So there's my two general answers, but now let's think about how we're going to get these involved. Is that easy? In order to find C1 and C2, is that easy to do? Well, remember that, 0 there is implying that t is 0. When times 0, x is 2. And so let's go plug all that in and see what happens.
Doug, I'm not sure if you know or not, but your camera's frozen and there's a few black boxes on your screen on the edges.
Oh. Let me stop sharing real quick and just try it again. Thanks for speaking up. I have two screens, and as you've noticed, from my perspective, sometimes one of the screens goes black all of a sudden for no reason. And right now that you guys all moved to the other screen for some reason, because my laptop screen isn't showing up and it hasn't shown back up. Did that change anything?
Yeah, the black boxes are gonna be your camera's still frozen.
Yeah, I see I'm black in there. I don't know why. That's okay. Thank you for letting me know. Let's see. So y of 0, if t is 0, y is -1. So that top equation, then y would be -1 and t is 0. Cosine of 0 is 1. And so that's C1. I'm looking at this equation up here. And then sine of 0 is 0. So that means C2 is actually multiplied by 0. So it's gone. And then e to the 0, of course, is 1. And so that -1/2 is just -1/2. And then there's a +1/2. And so that's cool. Those are gone. And so, hey, C1 is -1. Do you notice I sort of got lucky in that I didn't end up with an equation with C1 and C2 in it? So I now know C1 is -1. But I don't really understand how I'm supposed to get C2 because it isn't 0. C2 isn't 0. The sine of t is 0. So C2 could be anything at this point. It's not 0. But then, of course, I still have another option, my second equation. Let's see what happens down there. So x is 2 when t is -1. And so again, the sine of 0 is 0. So all this gobbledygook is just going to be gone because I'm multiplying it by 0. But then this over here, cosine of 0 is 1. And so everything else is kind of left behind. So I have negative C2 over 5. I don't know if it makes sense to, no, actually I don't think it does. So I have negative C2 minus 3C1 all over the top of 5. And so, cool, I think I'm home free. So then I multiply 5 both sides, I get 10. And I know C1 is -1, so that's a 3. I subtract that over and I get 7 equals negative C. Sorry, that's supposed to be a 2. So that means C2 is -7. So now I can actually kind of plug all that stuff in and write down Y particular and X particular. And so then we'll go take a look at the graphs and see if we're living happily ever after. So Y particular, and I'm going to throw of T back in there just because I think it's always cool to kind of note that. So C1 we said was -1, so that'd be negative cosine of T. And C2 is -7, so that's -7 sine of T. And everything else just comes along for the ride, -0.5. So barring any mistakes, that's true. And then if I plug those into this, let's see what happens with the second one. More going on there. So this is -1 minus 3 times -7. That'd be plus 21. -1 plus 21 is 20. 20 divided by 5 is 4. That's really nice. It came out as a whole number. So particular T, I get 4 sine of T. And what happens with this one over here? Well, negative C2. So that'd actually be negative, so that'd be a 7. Minus 3 times C1, that'd be plus 3. Oh, it worked out again. 7 plus 3 is 10 divided by 5 is 2. So that's just plus 2 cosine of T. So I think that is my answer. So again, it's not like that still isn't a pretty involved process, right? I gave you a little introduction to the project at the start of class, but it's 9 o'clock. And so we've been sort of at this an hour. So there's kind of a lot going on. So operator form. So we could not do this yesterday, and now we can based on operator form. That's kind of awesome. Let's see. And we won't go back and do this, but that's kind of my question for yesterday's problem. If I at least just stare at it for a second. That problem yesterday, would that have been easier if we did it in operator form somehow? Would that have made our life any simpler if I wrote that y prime as dy and eliminated variables that way? Maybe. I don't know if that would have saved time or not. So one thing I think is kind of important to point out, and I think my screwing up, making a mistake, I think made a difference. If you look at what was operator form, notice how you kind of have the X terms on the left side of the equal sign, and then you have the Y terms on the left side of the equal sign, and then equals the T terms on the right-hand side. Like that's kind of a good rule of thumb. And so, when I see this original problem here, to think, oh, that's the future. And so I'm going to take these and like move them over there. And I'm going to take these, oh, they're already over there, like leave them over there, like to do that first. And because that's kind of where this is going. That's what operator form is about. So again, if you're kind of a step person, we did operator form first, and then we used that to eliminate something. And then we really just sort of took forever to solve. So once we have, our equation that doesn't have x in it anymore, then we took the time, that third step, it's like solve. And then we finally got that answer. We said, okay, now what do we do? Well, then kind of the fourth step is we subbed it back in. So sub into one of the original equations. And then lastly, we came back and found C1 and C2. So if you're kind of a steps person, that's kind of what we did. Let's see. So just a second. I'm trying to decide if I want to show you this other cool technique or if you should just take a chill pill. Yeah, so 5.2, why don't you take, if you have your assignment, actually, I'll pull these up. I don't know if I can pull these up. 5.2, there's only 2 questions. And of course, doesn't that seem appropriate? Like how many questions are in the book? Well, there's probably a whole bunch, but man, that takes forever. And I don't know if I need that much practice. I mean, just a little bit might be fine. So I just want to stare at those maybe with you a little bit, but I'm looking at question 6 because that's assigned to you. And I think, yeah. Notice question 6, interestingly, that I assigned, unlike today's example, doesn't the top equation just has an x prime, but not a y prime. And the bottom equation has a y prime, but not an x prime, which means I might be able to do question 6 with sort of yesterday's technique of substitution. I mean, I think you can see that today's technique is superior because it works even if there's an x prime and a y prime. And so I wouldn't do it using yesterday's technique. But again, just a good straightforward question. And notice the directions say use the elimination method to find a general solution. So in other words, you didn't have to find C1 and C2, which is kind of nice. It just saves a little time. And then 32. 32 says in problem 31, and so it's a tank question. So can you write the differential equations yourself? So it sort of harkens back to what we did yesterday. It's a tank question, except for they just changed one thing about it. An interconnected tank problem. So you got to write your own equation and be able to solve it. Again, we're, scratching the surface. I mean, I look at this assignment and I think, wow, look how many questions there are. Oh, it goes to the next page. There's 39 questions. That's amazing. We have time to be introduced to some of these things, but notice there's a whole bunch of different questions. Or obviously some things take more practice. One thing I would like you to look at though, just out of interest, is look at question 25, 26, 27, and 28. What do you notice about those? It's kind of terrifying.
Yeah, 3 systems of equations.
Yeah.
Mhm,
You're not
3 equations.
able to look at it, it's like 3 equations, 3 unknowns. Can you appreciate that would be very doable? I mean, it's nothing I need to learn new. In other words, if I was just doing 2 equations, 2 unknowns in the way that you did in algebra before, and it was like 5x plus 2y equals 16, that kind of a thing. Sitting there for you to do. It just takes more time to, have 3 equations, 3 unknowns, reduce themselves down to 1 equation, 1 unknown. But still doable. So, that's something we could do. I think the coolest thing I'm inclined to show you, rather than do another example or, play around with something like that, or, even go back to writing your own questions. I think I do want to show you the Laplace technique to this, which I don't think your book even introduces, but I just think it's kind of fun to play around with this. And so let's do this. So I'm just going to say Laplace. because my overall goal is, again, just to teach you how to think. And so I think I gave you a pretty clear, slow example there that's going to allow you to solve just a basic problem. But what I want to do is just go back to this original equation that we were trying to solve. Because I just kind of launched into, a method to do it and said, let's do it this way. But I just like to think. And so this was our original question. So what would happen if you took the Laplace transform of both sides? Is that any good? And I don't know about you, but your first reaction to that should be something like, wait a minute, I don't know how to take, I'm used to Y's, but I'm not used to X's. But is it any different? I mean, remember, X is just a placeholder for some function of T that I haven't figured out yet. So let's try that. So equation 1, equation 2. So let's go down and take the Laplace transform of it. Equation 1. So let's see, 2 times the Laplace transform of X prime. Well, remember the Laplace transform of a derivative is, harkening back to the last test, it is S times the Laplace transform just of the function that we don't know. In other words, it takes the derivative away minus that function evaluated at 0. So it's no different. That's the point. It's like, oh, it's X instead of Y. It's just some function. So I guess then if I took the Laplace transform of number 1, both sides, then it'd be 2 times S times the Laplace transform of X minus 2 times X of 0. And notice I'm thinking, hey, X of 0, that was 2. I'm going to throw that in right now. And then the Laplace transform of Y prime, which would be S times the Laplace transform of Y minus Y of 0. Again, hey, I know what that is. It's -1. Equals the Laplace transform of X, which is the Laplace transform of X. And the Laplace transform of Y is the Laplace transform of Y. And what's the Laplace transform of e to the -t? I don't know about you, but I bet you're already kind of going, wait, I kind of forgot. I forgot what that is. Well, it was, I'm remembering it. This number right here is basically -1, and the Laplace transform of e to the junk is 1 over S minus that number, S minus -1. That'd be S plus 1. Now, that sort of looks terrifying, but again, this is really important. What's cool, even though it looks terrible and a mess, what's cool now that was not cool before? Maybe I'm asking you to read my mind, but I want
There's
somebody
no derivatives.
Exactly. There's no derivatives. Like, isn't that what this accomplished too when we did this operator form thing? We looked at the original problem. We said, dang, there's an X prime and an X. And so there's no way to get them together. And so with this operator form, we said, well, yeah, let's just write it as a D. And so now there is a way to get it together. So now these were both the same thing. It's like, yeah, this is junk times X and this is junk times X. And so we were able to put them together. Well, isn't that kind of what's happening here too? So this is kind of cool. Again, this is not in your book. This is not taught as a technique. I just think it's interesting to think about. So now all of a sudden, don't I have a way to collect together these Laplace transform of X's? And so I can actually collect them together. It's this very familiar. It has a ring to it. It's kind of like, yeah, didn't I do this? Isn't this look a lot like what the differential operator idea was? I mean, that's just kind of cool. So Sorry, I'm going type A here for a minute. For some reason, I want to get all of this on one line because it just looks like a mess. So awesome. Well, then I found myself thinking, okay, well, let's just, collect all the stuff together on the same side. So if I factored out the Laplace transform of X, then there'd be a 2s left behind for the one that I'm staring at. But then I would subtract this Laplace transform over. So that'd be a -1. And if I do the same thing with the y's, I'd have a Laplace transform of y multiplied by s. And then when I brought the 1 over from the other side, it'd be s -1. And then the only thing I have left over there now is that 1 over s plus 1. And then I got these constants like this -4 right here. And this +1. So let's see, -4 plus 1, that'd be -3. Added to the other side, it'd be +3. Did I make any dumb mistakes there? So is that doable? I mean, is that helpful? So I don't know if this is necessary, but I think I'll find a common denominator here so I can add those. So I guess that'd be 3s plus 3 plus 1. So it'd be 3s plus 4. If that's necessary. So this technique, if you remember, hung on the fact that, hey, all I have to do now is kind of solve for the Laplace transform of y. But the problem is I have 2 of these, right? A Laplace transform of x and a Laplace transform of y. So how am I supposed to get out of that mess? How am I supposed to make any progress if I have 1 for x and 1 for y? Who can tell us what to do? Here's a hint. Here's a hint. Well, I do have 2 things there. A Laplace of x and a Laplace of y, and I really don't want that. I want one of them. I don't care which one, but I just want one. Well, don't we still have a second equation? We just did that for our first equation. We haven't done it for our second equation yet. And so if I have 2 equations, then couldn't I use those 2 equations to eliminate one of those, like Laplace transform of x could be gone or Laplace transform of y? So let's do that. Let's do this second one. So let's see. So I'm just starting kind of in order here. Laplace transform of x prime. Again, I'm happy there's no coefficient in front of that. So that would be s times the Laplace transform of just x minus x of 0. Which again, we said was 2. And then plus y prime, the Laplace transform of y prime is s times the Laplace transform of y minus y of 0, which we said was, bam, -1. And then plus 2 times the Laplace transform of x plus just the Laplace transform of y equals the Laplace transform of e to the 1t. So that'd be 1 over s minus 1. And so if I continue with the same approach, then wouldn't I have the Laplace transform of x times s for this one, but then I have another one over there that's +2. So I just factor out the Laplace transform of x, leaving s +2 behind. Do the same thing with Laplace transform of y, leaving an s behind. And where's my other one? Right there. That's a 1 left behind. And then I just have these constants again. So I have my 1 over s minus 1, and then I have a -2 and a +1. This is -2, this is +1. That's -1. Add it to the other side, it becomes +1. If I again decide to find a common denominator, multiply this top and bottom by s minus 1, then that'd be s minus 1 plus 1. I guess it's just s then. So I'd have s over s minus 1. So hopefully I didn't make an algebra mistake there, but do you see how close this is to the kind of operator form? It's almost like, you know, s is kind of acting like the operator. I mean, it isn't. S was kind of a variable in another world, a frequency variable, we said. So instead of time, we're in the s domain now. We're now in the land of Laplace, not in the land of time. We're in the land of frequency. So can you use your basic algebra skills? Very similar to what we did. I'm going to give you a minute to do this yourself. Let's get rid of x again. Just so when I go do it, let's just make a decision collectively.
Are we going to be tested on the operator form, or could we use the Laplace for all of it?
That's a good question. My gut reaction to that is, I don't care.
Cool.
So you say that because you're kind of going, hey, I like this method better. Remember though, Laplace is kind of a mess. Like we have to still untangle something. What I'm curious about is, will I get the same answer, right? Because we just got the answer a minute ago. So I'm going to get rid of the Laplace transform of s for no good reason. Hey, my other screen just turned back on. Isn't that fun? You guys are all gone. So did you start this way, similar to before? Then isn't this term going to need an s plus 2, and this term is going to need a 2s minus 1? But if I do s plus 2, then don't all these need an s plus 2? Notice you fraction people, you're multiplying by s plus 2 over 1, so it would only be the top. So down here, if I multiply by 2s minus 1, I got to do it times everything. But so that's not that hard. So now I can multiply one of them by a negative, or in this case, I'm just going to subtract them just to kind of make you think a little more deeply. I'm just going to subtract those. I don't have to add them. I can subtract them. And by the way, why is it okay? I thought it was only, I want you to think about this for a minute, because maybe a few of you haven't thought about this before, but it's like, why is it okay to subtract two equations or add two equations together? That doesn't seem like it should be okay. I thought it was okay to add the same thing to both sides of an equation, or subtract the same thing from both sides. Like I can subtract 19 from both sides, or I can add 7 to both sides. Why can I add two equations together? Does that bother any of you? Have you ever stopped to think about that? Have you satisfied yourself? It's like, oh, that's okay.
I don't know. I guess I'd never really thought about that.
I
Maybe
hadn't.
because they're both connected in a way.
That is the answer. In other words, let's think about it with something a little simpler for just a minute. But it's like if I had 3x plus 2y equals 8 and 3x plus 7y equals 9, and you were wanting to subtract those two, but it's like, why is that okay to do? Well, here's the question. Is it okay to take this equation up here and subtract 9 from that side? Yes, as long as you subtract 9 from this side, right? But what if 9, isn't 9 equal to this? So then instead of subtracting 9 from that side, because 9 is not like x's and y's, I'll subtract what 9 is equal to instead. So it's like, oh, well, then why don't you just subtract 3x plus 7y instead, since, that's what's like this. And so you actually are just subtracting the same thing from both sides. But again, mathematicians will just, have you do it and not really stop to think about why that's okay. So you actually really are just subtracting the same thing from both sides. It's just on the right side of our equation, we got a bunch of s's, so it makes sense to do that. On the left side, we got a bunch of Laplace transforms. So let's think about what we get. I'll catch up to you. Don't I have then, so these are going to go away, but then I really have the Laplace transform of y. I don't know if this is a good idea or not, but you have s plus 2 times s minus 1. And for some reason, I'm thinking I want to multiply that out. So, that's what this statement is. And then I'm subtracting from it the one down below. And that would be 2s squared. Let's see, dangerous, plus 2s minus s, so it's plus s again, and then minus 1 times plus 1. And then, woo, man, on the other side, well, that looks horrible, frightening. I guess I just have all that junk minus all that junk, so I can't really think of anything I can do with it. So do you find yourself thinking, awesome, I'm on my home court, I know what to do now? Well, notice you have like terms on the left-hand side. So if I multiply that all out, I have s squared times the Laplace transform of y minus 2s squared times the Laplace transform of y. Isn't that just a total of minus 1s squared? And then s minus s is gone. That's kind of cool. And -2 minus a -1 is actually -1. So that simplifies algebraically. And then on the right side, I'm thinking, woo, this is not good. If I want to find a common denominator, I'm gonna have to add these. If I want to collect them together, I'm gonna have to find a common denominator. I don't know if I do, but let's see. That seems like a problem. Hopefully your algebra skills allow you to tackle this pretty quickly. So if I multiplied this out, I'd have 3s squared plus 4s plus 6s, and then plus 8. And that's over s plus 1. But if I want to find a common denominator, I'm going to have to multiply this also by s minus 1. And the other one will be the same or similar. Let's see, I'm going to write that as a negative sign. No. Yeah, I think I'm going to leave it as a negative sign for now. I'm always worried about negative signs because I'm going to forget to distribute and do something dumb. But on the top of that, I would have 2s squared minus s. But then I want to add these. So I'm going to have to multiply it by the s plus 1 it is missing. And in that way, I'm going to be able to collect all the junk together on the top. So that doesn't seem like a terrible plan. It's amazing. Like we're a long way out in the universe now, aren't we? So let's see. I know my denominator is s. Do I want to multiply the bottom out or leave it factored?
I think
should
your
be-
screen froze. Never mind.
No, my fault. That's weird. I wonder what's. Yeah, sorry about that. So now I'm going to distribute all this. And again, I'm going to dangerously try to do a lot of this in my head. So I got 3s squared times s, that'd be 3s cubed. And then I've got negative 3s squared plus 10s squared. So that's plus 7s squared. Again, this is why I make a lot of dumb math mistakes. So there's my squared terms. And then I've got 8s and minus 10s, that's minus 2s, and then 8 times negative 1. Hopefully I didn't screw that up. And then 2s squared times s, but it's negative. So that'd be negative 2s cubed. And let's see, s squared. And then I've got a minus s squared plus 2s squared. So that'd be plus s squared, but then the minus out front changes it. And then a minus s, which turns into a plus s because of the minus out front. So I think that's right. So now it's just a question of, can I collect all that junk together on the top and just have one expression up there? So I got s cubed terms, 3 of them minus 2 of them is 1 of them. S squared terms, 7 of them minus 1 of them is 6 of them. Minus 2 s's plus an s is minus an s, and then there's a minus 8. And so there's that statement. And then just move the, and again, I'm just kind of on the edge of my seat. Is this really gonna produce the exact same answer that I just got using the operator form a little minute ago? I always get kind of confused with negatives. So I'm kind of looking at that s squared minus 1, thinking, should I kind of factor out a negative 1 and make all the signs on top negative? For some reason, I'm kind of thinking, yeah, I think I am going to do that. So this turns into a plus, this turns into a plus, that's a minus. It feels less confusing to me. This is all just good practice. I mean, we're going toward a final at the end of next week. And so this is just kind of neat to put all of these things together, guessing techniques and Laplace transforms. And so then can you decompose this? Seems like it's time to change colors. So the s plus 1 would have that term. The s minus 1 would have that term. What What goes on the top of S squared plus 1? What's my guess up there?
CS plus D.
CS plus D, one lower. Now, by the way, for the first time, I just stopped to think about something. It didn't occur to me before, but what's this answer going to look like because of that S plus 1? Whatever's on top, maybe it's a 7 or whatever, but what's that S plus 1 on the bottom?
E to the negative t.
E to the negative t. So that's E to the negative t. This one is E to the t. And all of a sudden I'm going, oh my God, isn't that what we got before? Isn't that the answer we had? Wasn't our y equation? Didn't it have an E to the negative t? And then what about the sine and the cosine?
That's probably going to come from the CS plus D.
Yeah, because look what's underneath it. There's an S squared plus 1. See if I still have a Laplace table here. Laplace. Doug's table of Laplace transforms. Notice it's just S squared. Notice it's just S squared. So it's like, there's no A is 0. So that means this would be E to the 0t. Yeah, isn't that going to produce cosine and sine? So it's like, oh my gosh, I think this is actually working. We'll get back to that in a minute. That's pretty awesome. Oops, already been there. So that's pretty cool. This is actually looking like it's working. And so, in order to kind of compare this to this, of course, we've got to make them look the same. And so we've got to multiply by a common denominator. So in the rage to make sure I don't screw this up. Again, what does the A need that it doesn't have? An S minus 1 and an S squared plus 1. That's what it doesn't have. What does the B not have? It doesn't have an S plus 1 and it doesn't have an S squared plus 1. What does the CS plus D not have? It doesn't have an S plus 1 and an S minus 1, which I suppose I could write as S squared minus 1. Is that too dangerous? Not dangerous, but is it? You got that? I'm just multiplying those two together all at once. And so that's over my now common denominator. So now I can multiply all this out and try to get it to equal the numerator that's up here. And so this is kind of fun. So let's see, I'm going to have, again, this is dangerous. A times S squared, that'd be AS cubed. And then plus AS, I think I'm not, it's too close, I'm going to screw up. Minus S squared, except for there's an A in front of that. Minus AS squared, and then minus 1, so minus A. So that none of those collected together gave us 3 different terms. Same thing's going to kind of happen with B. I'll get BS cubed plus BS. That's convenient. BS plus BS squared. And then plus B times 1. On the others, the last one, I'll get a CS cubed minus CS plus DS squared. Squeeze it in. Minus D. Yeah. And so that's got to be equal to my other denominator, my other numerator, sorry. So in my organization, I'm thinking, okay, I got some S cubed terms here. What are my S cubed terms? I've got A, get rid of that. I've got an AS cubed, I've got a BS cubed, I've got a CS cubed. So A plus C plus A plus B plus C must be equal to that -1. I've got S squared terms. I've got a negative AS squared. I've got a B S squared. I've got a DS squared. And that's got to be equal to my S squared coefficient, which is -6. I've got S terms. I've got AS. I've got BS. I've got minus CS, and that's it. And that's got to be equal to my S coefficient, which is 1. And finally, my constant terms. Cont for constant. I've got a negative A. I've got a positive B. I've got a negative D, and that's got to be equal to my constant term, which was 8. So this feels like the matrix because there's too many things going on. Does it have to be the matrix? Definitely not. You could do all kinds of creative things here. I guess in the interest of time, I'm just going to quickly type that in. But I will say out loud because it's kind of important to understand. It's like A, B, C, D. Maybe I'll write this out for you. So there's 1A, 1B, 1C, no D's, and then -1. -1A, 1B, no C's, 1D, -6. 1A, 1B, -1C, no D's, and a 1. And then -1A, +1B, no C's, a -1D, and an 8. So there's my 4x5 matrix that I've got to type in. Second matrix really quick. 4x5 matrix. Hopefully I can type this in fast. 1, 1, 1, 0, -1, -1, 1, 0, 1, -6, 1, 1, -1, 0, 1, -1, 1, 0, -1, 8. Second quit, second matrix, reduced row echelon form. Matrix A for me. I got A is -1/2, which I'm very encouraged by. I wonder if you know why. B is +1/2. C is -1. D is -7. I'm very encouraged by those numbers because, I'm sorry you guys can see that, because that sounds really familiar. It sounds really familiar. So then I can say now that the Laplace transform of y is no longer equal to that big ugly black fraction. Rather, I can say it is equal to 1/2 over s plus 1, -1/2, because A is -1/2. B is +1/2 over s minus 1. And then C, S plus D. C is -1, so that's -s plus D, but D is -7 over s squared plus 1. So as I already noted earlier, of course, this is the Laplace transform of -1/2 e to the -t, which is a really good sign. And this, of course, is the Laplace transform of 1/2 e to the +t. But then I'm going to stare a little bit closer at this. And again, this is just as good practice. So let's go back and have a quick look. I know. Cut.
On the left side of the chart, you have a cleaner version of that.
Oh, God bless you, sir, for noticing that. Yeah, didn't we have one that didn't have E in it? Outstanding point. So much less work, right? Yes. Let's bring those over. I think that was Caesar that pointed that out, rescued us from my bad idea. So to get cosine, I just need an S up there. Unfortunately, I kind of have it, and it's already an S, except for it's kind of a -1, right? I gotta sort of think of it as factoring a -1 out front, leaving an S over S squared plus 1. And then I've got a -7, but what do I need up there? I don't need for this one, whatever this is, which for us, A is 1, I need a 1 up there, right? So how am I going to get a 1 up there? Well, again, factor a -7 out. So -7 times 1 over S squared plus 1. So sweet. So that would be -7. Let's see, how do I squeeze this in? I guess I'll just squeeze it in right underneath it. So this would be the Laplace transform of -7 times the sine of AT, or the sine of 1t. This would be the Laplace transform of -1 times the cosine of 1t. Hey, that's exactly what we got. So again, by inverse Laplace transform with both sides, notice our particular equation. Isn't it interesting? We got our particular equation. There's no C1s and C2s. And do you remember why that was? That's because way back here, when we first took the Laplace transform, we plugged those initial conditions in. So they were part of the problem. And so for that reason, we don't get a general equation. We just get our particular equation. So same exact answer. That's amazing. Yeah. So, but again, notice it's really cool that we got the same exact answer, and that, that as a method works. But it's not like it was any less work. I mean, this is still quite a bit of work, wasn't it? I thought it was. Same answer. Cool. So, but again, though, don't forget, and I'm gonna stop here because we're out of time anyway, but don't forget we're only half done. What would I do in this world? Because remember, we just succeeded in finding y of t. How am I going to get x of t now? Like if I was using this technique and kind of had to go back.
Get rid of Laplace of y. The same way
Yeah.
you get rid of Laplace of x.
Exactly. So one option would be start over. I randomly decided, I don't remember where I wrote that down, but I randomly decided, let's get rid of, I wrote that down somewhere. Now get rid of Laplace transform of x. We decided to get rid of, so start all over basically. Is there some faster way? Actually, I don't know the answer to this, by the way. Is there some faster way? So I now have the answer for y. I mean, I guess we could go do kind of what we did before. We could do what we did in the other method, which is plug our value for y back in. Now that we have y, we could plug y here and y prime there, but we'd still have an x prime equation. But we could multiply this equation like we did before. We could multiply this equation by 2 so that we could subtract them and get rid of the x prime, and then have an equation with just x's, y's, and y primes, and then plug it into that. I mean, I would be inclined to do that, like switch over to kind of the other method rather than start completely over if my goal was just to kind of be done, but that's just an interesting side point. So I guess I'll just add that thought to the bottom and we'll call it. One option, now redo with the Laplace transform of x, or sub yp back in to the original equation, or equations, however you choose to do it. Those would both be kind of workable. Awesome. Well, how's your brain? Not sure why I don't have a camera, but
I feel like we thought the Laplace transforms by themselves were long, and now we just have a ton. Like the problems seem to take for like multiple pages.
Yeah.
yeah. So it
I
isn't.
cannot wait to make algebra mistakes again.
I know. Doesn't it feel like there's no way you can get these problems right? And I mentioned this, but like on the last test, I was able to find everybody's mistakes, and that's all they were. It was just like a little lost a minus sign, especially the Laplace transform when you multiply a number in, and there's a negative already in there. It's like it's so easy to screw that up, and you don't worry about that stuff. And again, that's one of the reasons on the last test why I made the questions worth 12 points, because if that was your only mistake, and I told you this before because I had a couple people do it. If you only made one little algebra mistake and at the bottom you said, this doesn't check out, I don't know why, then I didn't take any points off. But if that was your only mistake, was that little algebra mistake, I only took 1 point off. So you still got 11 out of 12. And a lot of people made 2 or 3 of those tiny mistakes, effectively missed 3 questions on the test. But it's like, that doesn't deserve to be, a really bad grade, unless of course we were building a bridge and it fell into the ravine with a bunch of cars on it. Doesn't really matter that it was an accidental mistake. It's still an F.
Yeah, if we ever had to build a bridge in a 2-hour time limit, we'd be screwed for sure.
Yeah, you have 2 hours to build a bridge. That's why I keep talking about checking your work, and the fact that like we get these answers and we could go clear back to the start and plug them all back in. We never checked it that way, but obviously if I was doing something really important, you'd have time to get to the bottom of whatever went wrong. And of course, with the advent of computers, are you really even needing to do this? I think it's kind of cool to understand the language of motion and how you're able to model like the project catenary curves and so forth, things that are real, because that's what bridges are based on, can be anyway. Like suspension bridges can be based on catenary curves, and being able to kind of feel like, yeah, I understand all of that. Maybe there's modeling software that I don't really have to worry about that too much, or some automated processes that allow me to do some things. And coincidentally, that's exactly what I'm going to show you tomorrow. Euler's technique to sort of get an answer, like we found the equation just now for y of t, and that's really cool because now we own the relationship and we know anytime I want, what. But remember that having the equation is not useful. It's having the equation to use it for something. In other words, now that I have it, the only reason I have it is so that I can say, awesome, now I need to know what happens at y of 3, right? I'm going to throw in 3 seconds, and then that equation is going to spit out what y is. And that's what I actually really needed to know as an engineer. I don't need the equation. I need what the equation can give me. And in the end, Euler's technique allowed us, when we used Excel, to creep really slowly. Remember a long time ago, we crept really slowly along the curve, and we actually found the graph of the curve without knowing what its equation was before. And if you have the graph, it allows you to kind of predict the answers. Well, we're going to do that for second order equations tomorrow. That's what 5.3 is about. And so, again, the argument can be made, we can skip all of this if we're actually building a bridge, because all we really need, we know that y of 0 is 2, but what we need to know is y of 3. And so the question is, could we creep along the unknown y graph, or the y equation that we just found? We don't even know what it is, but yet could we creep along it and actually work our way to the place we want to get without even knowing what the equation is? And so thanks to modern techniques, and even something as simple, for us, simple as a spreadsheet, but you can appreciate what's that going to look like to the people that invented this stuff. We can actually answer that and never even know what the equation is, or at very least just have another cool method to kind of check our work. So I'll show you that tomorrow. All right. So if you want to ask me any project questions, even if you just want to sit here and I showed you kind of a shortcut or a trick. I showed you a hint at the start of class. If you want to spend 5 or 10 minutes and like try to make progress with that and be like, okay, I see it now. All right, I think I got it. And then seeing you're gone. You're more than welcome to do that, because I really, it's due tonight. So are you guys cool? Because I want you to enjoy these, not suffer. I mean, obviously it's going to be some suffering, but are you like asking me for, can I have one more day? Can we meet together at 5? I mean, don't be afraid to ask for what you need. Worst case scenario, the answer is no, but it's our last project. I really would like you to get it.
Personally, I think another day would be cool because I get burnt out pretty quick trying to do the algebra on it. And I've
Yeah, I
tried
was
about
gonna ask
3
for your
times.
algebra Hawkeyes, because I caught one mistake, but I don't know if I ended up going in a full circle. I don't know if it was on accident or not. But it kind
Yeah. And I would love to help troubleshoot stuff and, you know, give you an individual hint if you're stuck someplace, some of those kinds of things. I'd love to do that. So yeah, share your screen, Martin. Do it right
Okay.
now. Yeah. And I don't see any reason why we couldn't make this do not tonight, but the next day. So I'll go into my open math right now and do that. It's not holding us up for any particular reason.
Sweet, thank you.
Okay, I am staring at what is very beautiful work. Martin, so he. So the Laplace transform. So you tried to take the Laplace transform just like it sits, like before kind of doing anything else to it. Oh, he just disappeared.
Oh,
So I'll have to come back.
Hey Doug, were we required to find both of them or just one?
Both. And that's actually not that terrible. One of them will come from guessing.